Let me introduce myself. My name is Dan Christen. I'm the director of the Center for Doctoral Training in the Mathematics of Planet Earth. And I would like to welcome you all to this panel discussion on the subject of numbers to the rescue, can math save the planet? Before I start to say a little bit about what is the object of our discussion and why we are all here, I am instructed that I need to do a bit of flight attendant exercise to mention the fire exits. And there's one over there, and there's one over there out to the back. And also that you can tweet about the session using the hashtag #MathsForThePlanet. And do not ask me what this means. I'm just reading from this piece of paper. Right, so now that this is over, I can just turn my attention to the reason why we are here. We are here to have this panel discussion on the title that I just mentioned, and with the scope to initiate a dialogue between mathematicians that are working in academia and the industry, and also mathematics users that are using mathematics both in the academia and outside the academia, in services, in the government offices, and in the industry. So, you know, we have in the panel and also in the audience members for all of this, from all of these parts, and it is our intention to try to initiate a dialogue, and in particular to initiate a dialogue between the Center for Doctoral Training in the Mathematics of Planet Earth that has started its activities 3 years ago following an initiative from the Engineering and Physical Sciences Research Council. This was a new initiative with the aim of training mathematicians in the mathematics of planet Earth, to train a new breed of mathematicians and scientists that will be able to tackle all the problems that our planet faces today. And we would like to invite a dialogue. We'd like to start talking to the industry. We'd like to invite people, members of the industry, to talk to us and tell us if they have interesting problems, if they have problems that they see that they can be perhaps put forward for our students, our future graduates to solve or to work on them. And this is a very large center. In the next 5 years, we will have 70-odd graduates. So it's a powerful force of talent, a powerful pool of talent that we put forward, and we invite the industry to come and see how they can use them. I guess that's all what I wanted to say. I'm going to also mention what's going to happen next. So I'm going to invite Joe Hay in a minute to give a brief presentation of the Grantham Institute. The Grantham Institute is a co-organizer for this activity. And then we will have the discussion, and at the end of this discussion we'll have a reception which will take place next door. And during the reception, members of the panel and members of the audience will have the opportunity to talk to people that work for the center, to talk to the students that are among the audience, to see some of the posters that students at the Grantham Institute and the MPE CDT have produced, to see the kind of work that we are doing, and to sort of initiate, as I said, a dialogue. So thank you very much, and I'll invite Joe Hay to introduce the Grantham Institute.
Thanks, Dan. I won't prolong the introduction too long, but it's a great pleasure for the Grantham Institute to co-host this event here today. So for those of you that don't know, the Grantham Institute is the Imperial College Institute for Climate Change and the Environment. So we act as a hub to support and encourage research in climate change and environment across the whole college, and to do interdisciplinary work and get people talking to each other, to translate that research into real-world impact, to have real effect, and also to communicate the results to policymakers. So that's our remit. We also coordinate a doctoral training partnership, which is similar to the CDT and Mass of Planet Earth, but it's much broader in topic, so it covers everything to do with climate change and the environment, so that would be including from earth sciences to physics and maths, computer science, engineers and everything. And so we have a very wide range of students, but most of them will be using maths to a certain extent or other. And they're also very keen on engaging with stakeholders and industry. So there's some DTP students here. Anyway, that's enough about the Grantham and about the DTP, and I'll pass over to Brian Hoskins, who is the chair of the Grantham Institute and who's going to chair the panel here tonight.
Thank you very much, Joe. And I apologise that mathematics wasn't able to sort out the weather tonight, but no doubt it can sort out the planet later on. So we have 5 panellists here who are going to help start the topic off, and the last bit will be very much an interaction with you, the audience. And to save time, I'm not going to introduce them all now. I will just very briefly do it one by one as they talk. And so without further ado, they're in this order. We've actually managed to arrange that. And the first speaker then is Alistair Forbes from the National Physical Laboratory. And over to you.
Thanks, Brian. Welcome, everybody. Nice to see you. So I work at the National Physical Laboratory, which is the UK standards laboratory. So our role is making sure that measurement in the UK is traceable to standard units like a metre and a kilogram. And you know, the metrology community has been very successful in promoting standards in engineering disciplines. The fact that we've got global manufacturing now is a testament to that success. But when we talk about traceable measurement associated with societal challenges such as climate, then we're dealing with models and systems that are a lot more complex. And I think we have to expand our ideas of traceability, uncertainty, quantification to take into account the fact that we've got measurement data that we're hoping we can trust, but we've also got complex models that we're using to interpret that data and making decisions at the end. And a lot of uncertainty that resides in the model. I mean, George Box, the statistician, said all models are wrong, but some models are useful. And that's essentially where we are in this complex arena. So traceability has to extend its sort of concepts of uncertainty quantification for addressing some of these societal challenges. So the question is, you know, can mathematics save a planet? Well, I think that the extent that science can help save a planet, then mathematics has to have a role. All scientists have to interact with mathematics to some extent. So the question is, do we need mathematicians? In my mind, do we need mathematicians? Do we need me? I'm a mathematician. And you know, physicists and engineers are very capable of doing a lot of work. What's the mathematicians doing to the bringing to the party? Well, I think the solution has to be multidisciplinary. And I think mathematicians are reasonably well placed if you've got the right engagement type mathematician who's able to interact with the different team players and try and bring common understanding. Try and bring some abstraction and conceptualization, trying to understand what the core of the problem is rather than getting too confused with some of the details. So conceptualization and communication. Also developing a narrative to make sure that people understand the problems and are able to think they can do something about it. Quite often people are disengaged because they think that it's somebody else's problem, or you know, it's just too difficult for me to deal with it. But we all have a stake in it, and we all have to try and engage with that. So there's these soft skills that I think the mathematicians have to have in terms of communication, developing the narrative, developing the right concepts to help that narrative. And then there's the sort of hard skills to do with analysis, computation. I think we all know about Moore's law, but over the last 50 years, the progress in algorithm development has far outstripped the progress at Moore's law. Okay, we've got faster computers, but we've got far better algorithms. Our understanding of the analysis of the problems is far better. And we can solve problems now that even 5 years ago we thought were just about impossible. And so we certainly, mathematicians have a role to play in trying to address some of these hard things. These solving equations that weren't solved before. But I think bigger picture is trying to develop that and being part of developing that narrative. Thank you, Brian.
Thank you. Thank you very much, Alistair. And there'll be plenty of time to come back on some of these points later on. So the next in line then is Alan Thorpe, who's just retired as being Director General of the European Weather Centre, the European Centre for Medium Range Weather Forecasting. And previously he was Chief Executive of NERC as well.
Okay, thank you, Brian. I want to answer the question, of course, in the affirmative. Maths can save the planet. And I just wanted to say a few things about the role of mathematics in weather prediction, which is the sort of field that I've been involved with for most of my career. Weather forecasting, weather prediction is really vital to lots of people and the economy every day. People rely on the weather forecast. But also, if you want to understand climate change is none other than climate, is none other than the progression of hundreds of weather systems all over the globe. So our understanding and knowledge about climate is only as good as our understanding and knowledge of the weather. So I wanted to say a few things about how mathematics has been really important in the development of weather prediction. There's really been a revolution in weather prediction over the last 40 years. And it's been driven by science, and it's been powered by mathematics. And it's really a sort of scientific success story that in many respects has been hidden from the public. And in that respect, it's a sort of quiet revolution in science. Weather forecasts come from the use of numerical models, and those models are used to solve the partial differential equations that govern the motion and development of the atmosphere, encapsulating Newton's laws of motion and the laws of thermodynamics, and applied to the atmosphere. So very much use of numerical models, as Alistair has mentioned. And the concept of creating a weather prediction is by analogy with medicine, actually. We start with understanding the current state of the atmosphere, which is called, in the jargon, the diagnosis of the weather. What is the weather like today? And then we use the numerical model and the laws of physics to predict what the future evolution of the weather and the atmosphere is, which is the prognosis of the state of the atmosphere into the future. And that way of describing using the mathematics and physics dates back to the start of the 20th century, when Wilhelm Bjerknes and Henri Poincaré really set the agenda, physics and mathematician together. Of course, back then in 1900, although they could set the agenda, there was no known way to observe the atmosphere globally to be able to address this problem, and there was no known way to actually solve these equations because there were no computers or anything analogous. So really, over the years, mathematics has been at the core of this revolution. First of all, in describing what the current state of the atmosphere is. We've really had to use a lot of the new satellite measurements all around the globe. The current weather forecasts every day use something like 40 million observations all around the globe to start the initial conditions of the forecast. But of course that's not enough, and we've used an approach whereby we use an estimation theory approach where we have a prior estimate of the state of the atmosphere using Bayes' theorem essentially from an initial forecast. We merge that together with the observations to get the best picture of the current state of the atmosphere. And the mathematics associated with that merging of the observations and the prior estimate is seriously complex mathematics involving a global minimization of the difference between the observations and the initial guess. And that mathematical approach has been very powerful. We also use, of course, mathematics to say how to solve these partial differential equations because there aren't analytical solutions. We have to use numerical methods. That's a whole branch of mathematics in its own right. Another fundamental insight that's used comes from Poincaré's idea in 1900 that actually if you had some uncertainty, some error in your initial conditions, that would grow rapidly and produce a very bad forecast. It would actually pollute your forecast. And to understand how nonlinear mathematics enables these small perturbations, these errors in our understanding to grow over time is encapsulated in the theory of chaos, which Ed Lorenz and others have developed. And so each day now, weather prediction is not just a single weather forecast, but it's actually 50 separate realizations of the atmosphere to try and span the uncertainty, to have confidence in what's likely to happen. And finally, in this mathematical input, it's actually using the supercomputing to be able to solve these equations and to manipulate the data. These are huge data sets, and the data has to get into the computer, it has to be moved around and to be analysed, and then to be disseminated afterwards. And that big data problem and supercomputer problem involves mathematicians and computer scientists coming together to really understand that problem and to improve on the algorithms that we have. So in conclusion, there's a huge amount of mathematics in weather forecasting every day. It's the same kind of approach that's used to simulate the brain, or to simulate the evolution of galaxies, or even to simulate the economy. And these global and big computing problems are really important. So weather prediction has moved on. I've called it a revolution because in 40 years, the last 40 years, if you wind back 40 years, we can predict with confidence about 2 days ahead. Today, every day we can predict with pretty good accuracy out to 6 or 7 days ahead. That's been a huge improvement in our ability to predict the weather. But it's not good enough because we still have major weather events that affect people's lives called natural hazards, which are not well predicted. And so we have to improve on this, and particularly we have to get more observations to apply to this problem. We have to be able to have higher resolution models that describe the details of these weather systems. So my story is we've had a huge improvement from mathematics and science in this field, which has been useful to everybody, but we've got a lot further to go, and mathematics can really help us to do that.
Thank you, Alan. And everyone's keeping to time very well, so we move on to Paul Favre then from the satellite catapult, applications catapult, sorry.
Thank you very much, Brian. So we've heard from a mathematician and some very eminent scientists. I'm an engineer, so I'm looking for real-world problems and how to solve those. I work for the Satellite Applications Catapult, and we've heard a little bit today about how satellites can help to gather the information that informs perhaps not only the weather services, but also climate services in the future, and how do we predict what the change in the climate is actually going to make an impact on future weather systems and the impact on industries as well. So I'd like to beg the question, when we're asking, can maths help save the planet, what do we really mean? Do we mean save the planet? Do we mean save the society and the economic systems under which we operate in the society? And for that, if we think about the industrial aspects, how do we make sure that we can actually still function as a society? What does it mean from an industrial context to keep operating and providing services? And that's really key, and it really comes down to the heart of what the Satellite Applications Catapult is about how do we add value. So if we start to think about the industries that may well be affected by the changes in climate or the extreme weather systems, that extends all the way from what are the impacts on fishing and aquaculture, what are the aspects on forestry and agriculture, what are the aspects on infrastructure, whether that be energy systems or water systems, for instance, the freshwater aspects. There's a whole range of different areas where there are industry providing services to society that are going to be affected and are affected operationally by the extreme weather systems. So I don't want to just know about the probability, I also want to know about, from an engineering perspective, how are we going to deal with the consequences, and what do we need to do, how much margin to be putting into the system, and how do we respond to those challenges. And that's where some of the mathematics in terms of the modelling of the probabilities can also start to apply them to the way in which you deal with the consequences. So in order to inform those decisions, the operational decisions, you need to get data and you need to turn it into actionable information. Some of that data might come from satellites. So you'll be familiar with the Copernicus missions, generating essentially a whole range of different services in terms of Earth observation data. That might not be sufficient. You have to effectively get that data and feed it into the models of the climate of the weather systems. what does it mean to actually create an effective model, an empirical model? What data do you need? How can you be sure that it's effective in terms of actually driving the model forwards? So that needs some ground truthing. It needs the models to be refined continuously, but potentially also you need to gather data from the environment. This becomes a very significant problem when those data systems are very remote. Actually, you don't want to gather the data. You want to gather the specific parts of information that drive your empirical models and drive them forward reliably. And that brings its own challenges with regard to the models, the mathematics, the mathematics of information. So I think one of the questions, I'd like to come back to the question again, is it really saving the planet, or is it making sure that we can actually continue to serve industry and actually make sure that it's sustainable in terms of actually the operation of society on the planet today? Thank you.
Thank you, Paul. And number 4 in line then is René Aid from EDF.
Thank you. Thank you, Lieutenant. Thank you for being here. Can you hear me? Yeah. So my name is René Aid. I'm from EDF Research and Development, from the Research Center in Paris-Saclay. And EDF Research and Development is 2,000 people working on all the aspects of the electric system, going from consumption to generation and network. So I guess that if I'm here, it's because you know that energy, providing energy to the public, is a main activity which is very dependent on climate. It is dependent on climate both from the consumption point of view and from generation point of view. You know that if during winter, if the weather goes bad and if it's very cold, then people are going to need more heat. So electric heating or even gas heating, but they are going to consume more. And I don't know if you're aware of this, but the electric system is more and more depending from the generation point of view on climate issues. We are introducing much wind farms, much solar panel, and wind farms depend on the presence of wind, and solar panel depends on the presence of solar. So the hazards and the dependence of the electric system on climate is increasing to cope with the climate change issue. And so, as the former panelists told about, we are mainly concerned about developing our business and maintaining sustainable business with the issue of the climate change. So all the risk assessment we do many kinds of risk assessment, financial risk assessment, physical risk assessment, and industrial risk assessment. Financial risk assessment, each time the weather is very cold, it costs us a lot of money to bring peaking load power plants to satisfy the demand. So it costs for us. Physical risk assessment. All what we do, we have to keep margin. You know that electricity cannot be stored. Even there are batteries in the system, there are hydro reservoirs, but electricity cannot be stored. And so the only reserve that we can have is to get more capacity. And so we have to hold more capacity to satisfy demand. And so we have risk assessment, physical risk assessment, to be able to satisfy the demand with a certain level of probability. And the last risk assessment we do is industrial risk assessment. We have industrial installation, many power plants, network everywhere, and so they have to be reliable and to sustain many climate risk. I give you an example. You remember the heat wave in 2003. With the heat wave in 2003, suddenly 15 days of weather above 30 degrees in France. So then, unpredicted, it killed 15,000 people in France. It destroyed part of the distribution network. The cable melted. It was so heat in the ground, the cable melted. So it was a disaster. But there was another disaster. Remember the tempest in 1999. Tempest in 1999, wind during one night above 180 kilometers. During several hours, it destroyed part of the transmission network. So we have to handle this situation, and we know that in the future, there's going to be more events like this. But all the information we have is based on historical data. All the risk assessment we do is based on historical data. And so we need to have now, we know that's going to be different in the world, we need to have modeling aspects to introduce in our risk assessment things which are not being observed yet. So we need to have climate change model and a climatic model. And one thing which is much more important for this, we are interested in the global change and the +2 temperature criteria and targets, but we are interested in local effect of climate change. We are interested in what's going to happen in the Gulf de Gascogne. You know, we have power plants there, and the power plants depends on the temperature of the water. It depends on the temperature of the water in the rivers. So we need to know what's going to be the level of the rivers in 50 years from now. And now we are building wind farms in places where there is wind. But you know, wind farms, they produce when there is wind, but they stop to produce when the wind is too speedy. So we need to know what's going to be the risk of not adding electricity from wind farms. So I don't know if mathematics in general can save the planet. But what I'm sure is that mathematics maybe can save our business.
Thank you, René. Well, we're all dedicated to that. So now we move on to Eric Van Sabeel, who's going to take us from here.
Yeah, so I'm a lecturer here at Imperial College. So the question is, can mathematics save the planet? Well, my answer would be, well, they better should. The planet is in a dire strait, from climate change to biodiversity loss to plastics in the ocean. There's all these problems that are now really coming together and creating a very hostile situation for not only the planet but also society, and also, indeed, as we heard, economics and businesses. So mathematicians live on this planet, and they live on this planet with a whole bunch of non-mathematicians. And I think one of the key things that mathematicians need to do is to explain what they understand and explain what they do. Now the good thing that we mathematicians have is that all of what we do, and especially in terms of climate change and the environment, is complexity. Now we call it complexity, but to somebody in the general public it is magical. And that is a disadvantage, because it means maybe that they don't really understand it, and magical is complicated, but it can also be a big advantage, and I think we don't harvest that enough, because the public loves magical things. The public loves thinking about things that they don't understand and that they really want to explore. I guess the butterfly here is one of the really key concepts, the butterfly of chaos, which you can use in so many ways, which you can use in so many understanding contexts, whether it is from a missing plane somewhere in the ocean and why we can't even find our plane somewhere in the Indian Ocean, all the way to, indeed, the more traditional hurricane models. So I guess that mathematicians don't only need to solve the planet, they also need to tell how they are going to do it, because only then can they get the rest of society on board, and can we do this together? So a mathematician doesn't only need to be a team player and doesn't only need to be multidisciplinary, they also need to be pretty extrovert, I guess.
Thank you, Eric. Okay, there's a challenge for the mathematicians, right? So I think we've heard various aspects about the role of mathematics, the input to decision-making, and the input to managing the environmental problems around. And we've heard that mathematicians can't do it on their own. They actually need to interact with other sciences and social sciences and economics. And they also need to interface with business, with the policy world, with the media, and with the public. And just before, I think in 10 minutes' time, we'll probably open this up to you all to ask some questions or pose some thoughts of your own. But let me just ask the panel if anyone would like to come back, having heard what the others have said, or indeed perhaps thinking a little bit wider. Would anyone like to come back to the scene? Oh gosh, you're all so satisfied with what you've heard from everyone else.
Well, I can
Right, come on, let's do it.
perhaps say that one of the things about the last 50 years is a sort of interaction between the mathematical community and the statistical community and the computational community. I think the role of statisticians and the data scientists has been crucial as well. So I think that has been very important. And somebody was saying earlier on today that actually the mathematicians are changing as a breed, that we are becoming a lot more engaging and willing to interact with the world outside. So we're not just proving Fermat's theorem and things like that in our own offices. We are engaging. And there's a question of whether or not the role of mathematics is properly perceived by the public. Mr. You already mentioned it, that the fact that we've got far better weather forecasts now is a success of mathematics and computation and statistics. And so I think we probably need to encourage the mathematical community to say, actually, your contribution to society and addressing these societal challenges is important. And it's something that you should really want to engage in.
So there's a bit of an image problem here, isn't there?
Well,
everyone thinks of the pure mathematician just thinking about their lemmas and...
Yeah, sort of yoga with numbers,
One of the things that's quite interesting is perhaps the cost of doing mathematics. We talk about doing the computation for weather systems moving forwards and prediction. Actually look at the size of the computers and think, actually, we're warming the planet up quite a lot. Perhaps we should be thinking about how do we do things slightly more efficiently. And I was very encouraged by the fact that the algorithms are getting more efficient, because the computers might be getting efficient, but they're also getting very power hungry. One of the things, before I hand off, I'd like to bring to your attention is if you think about the aspect of data, I touched on big data, if you like. If you look back through the history, the concept for actually starting to process information when we had digital computers and things is, it's been continuously evolving over the last 50 or so years, and we've heard about Moore's law. If we think about this for a second, where does the data come from? It comes from sensors. The sensors create the data, it needs to be stored, it needs to be processed, and then the information needs to be moved around. So there's actually a number of different trends that are involved in this process. There's the trends in terms of how much data you can generate from sensor networks, and that's really growing very, very fast at the moment. You just have to look at the things that you carry around with you, and the whole aspect of what cars are going to be doing in terms of being able to generate data as a sensor platform in the future. The cost of storing the data, which is falling all the time, it's actually falling faster than the cost of computing. So you actually got a rate of advances in terms of storage, which is vastly increasing, greater than computation. And you've got the cost of moving that data around, which is also changing. If you think about the 4G networks that you might have now, or your broadband networks at home, but it doesn't change as fast as some of those other dimensions. So from an engineering perspective, the optimum point changes all the time. And trying to model that in terms of how do we do it efficiently, how do we make sure that we don't burn up the planet, just trying to work out the maths.
Alan.
Yeah, I'd like to pick up on that point because, as you were saying, the cost of computing, the size of supercomputers to solve these big modelling problems is becoming a very important and difficult area. Moore's law has been great, but we're kind of running out of it now because the individual processors are not getting that much faster. All that's happening is that the computers are getting bigger and bigger with larger and larger numbers of processors consuming more and more power. And one of the challenges for mathematicians and computer scientists is to be able to devise algorithms that actually utilize these massively parallel computers. The computer at the European Weather Centre, where I was until recently, has 180,000 processors in it. And probably in 5 years' time, the next supercomputer may well have over 1 million processors in it. And moving information around that is becoming the major bottleneck, actually, to this. And really the resolution of the information we had from EDF colleague, that it's really the local information that's really critically important. And if we're going to be able to do that problem, we've got to be able to utilize these kinds of computational problems much more effectively than we have. And that's a core, a mathematical problem. I'm a great believer that supercomputers, not just a tool, it's actually an integral part of the science and of how we do these problems. So I think it's a really fascinating and critical interface.
We've heard about interfaces with industry, perhaps a little bit more. Can we tease out the interface with industry? How does that work? Is it working well? Paul's told us something about that, but...
Yes, so now I guess my micro is working now. No? Yes. So we are a large consumer of simulation of high computing, high performance computing, both for, we are not running a climate model, but we work with Météo France, we work with your center to have a prediction and to have 50 scenarios to assess, to make our risk management, to make our risk management assessment. And so there is quite an interaction between climatology and our business. So, and we work much on that, and we work much on, I said, on local modeling of what's going to happen in certain region of France or certain region of England, because we have main asset here. You know EDF Energy? Yes, you know EDF Energy. Is EDF Energy one of your provider? Yes, okay, so you know EDF Energy, and so we are very, very what's going on. Yes, you know that, it's in the paper. You know we are trying to build something here. So we are very, yes, we're going to make it. But we are very concerned about what's going to happen also on the climate, on the water reserves here. And in France, you have to know that we have some nuclear power plants which is in the southwest of France. And in the southwest of France, if we believe the long-term forecast of climate, the southwest of France is going to be in the climate like Morocco. So, it has an impact on the water levels of the rivers. So we work a lot on that. If you may, I would like to add a word on the challenge of mathematics. Because the title of this panel is Can Math Save the Earth? And so I guess if we want to save the Earth using mathematics, there is one aspect for which all you learn during your studies of fluid mechanics, of partial differential equation, of modeling, all you learn can be used also in economics. And it's the main challenge that we face together as a whole, as a planet, as humanity, because if all the nations agree on COP21 to sign a paper to reduce carbon emission and to achieve the target 2, you have to be aware that in fact it's very difficult as humanity to make all these people go in the same direction. You have to understand that there are many interactions, many conflicting interests, and to take into account this conflicting interest is the key issue to make the decision maker, the political decision maker and the business, to give them the right incentives to achieve a common purpose. And this is the main challenge. You should not think that somebody is going to give to everyone an order and everybody is going to achieve the common good. In fact, everybody is looking for its own interest because everybody has his own constraints. The businesses, the states, they don't have the same situation, and you have to take into account all these particular situations of all the countries to understand why they behave like they behave, and to understand what they do. I will give you an example. Jean Tirole, the last French Nobel Prize. As other people, they are trying to model the interaction of the states in the negotiation for the carbon reduction emission. It's a negotiation between 140 countries. And everybody, the big ones, they are thinking ahead. Once they go to a negotiation table, they think to the next round. They are anticipating agents. So now you try to make some modeling of a game with 100 people who are all strategic. If you know a little of Nash equilibrium, the combinatorial effect is explosive. So you cannot handle this kind of problem with this. You can try with a supercomputer. But the other way is to model things like you have a continuum of agents. And then you can model things using partial differential equation. It's one main, I would say, advances in economic modeling that has been done in 10 years before by two French mathematicians and also Canadian people who try to model the interaction between anticipative agents using continuum main agent, and partial differential equation. So what I want to do, and what I want to stress, is that if you want to use mathematics also to save the planet Earth, there are two things we can do. To tackle climate change in its baseline using climate modeling, but all you learn from this, you can also use it to try to model the interaction between states, between economic agents, and to give them the right incentives to achieve a common goal.
Okay, I think that's a suitable note now to open this up to you, the audience, to raise questions, please, or very simple points. Please don't make a speech. And we'll collect 2 or 3 and then throw them to the panel. So if you want to direct them, do, but let's probably make it open. So yes, number 1 there, number 2 there, number 3 was there, was it? Somewhere? Was there a hand there? No, okay. There's 1, 2, okay, and 3 over there, right.
Thank you.
Thank you. Julian O'Haran is my name. You've tended, all of you I think on the panel, to focus on the application, the usefulness of maths or use of it in trying to predict the weather and the climate and to work out how we can curb climate change, you know, by public involvement and government policy. But what about a much easier, you know, the weather is right up there in the sky. No wonder it's very difficult to get it right, and occasionally people get it wrong. But what about just trying to predict something as simple as how much a new bit of kit to generate some electricity will cost and how many years it will take to build?
Okay.
How far has maths been the problem in the difficulties which are causing EDF to tear itself apart at the moment with different predictions
I
about
think we'll
the
ban
EPR.
Renee from answering this one.
How far has maths been a
Okay, thank
factor
you,
in that?
Julian. Yep, thank you. And number 2 was there, and if that one could go across to number 3 over there. So, sorry, could you get the microphone over there too? Yeah. So number 2 is there.
Thank you, that was very interesting. So in terms of climate change mitigation, which to be concrete about this means going from about 10 billion tonnes of carbon emissions at the moment to 0 sometime around 2070 and then possibly net negative. How can maths help achieve that? Because if you read reports about how to mitigate climate change, it often talks about carbon capture and storage or decarbonising electricity generation or electrifying transport. So my question is, how can maths help with CCS, or how can maths make renewable generation cheaper or buildings more efficient?
Okay.
Thank you.
Well posed. Okay. That's number 3.
Philip White, UK Trade and Investment. I have a question for Dr. Aid. In short, the question is there a role for extremely local and short-term weather forecasting in helping you manage a smarter grid?
Yes.
Because you have to ramp up load generation very quickly or shed load very quickly when clouds come over or the wind drops. Is there a gap in the information you're being provided, extremely local and short-term, minutes even?
Okay. Fine. Thank you. Right. So we have 3 there. Who would like to start the first one about the cost of simple problem, such as cost of electricity and the time it takes to build a power station rather than these complex ones? I don't know whether you want to handle it, Renee, or not.
Depends.
Is anyone else wishing to have a go?
We are very, very solidaire. Okay.
So is it a simple mathematical problem to work out?
It's not exactly my field of expertise, because I'm rather microeconomic, and this is my colleagues from nuclear. But I guess for the cost of Hinkley Point and the difficulties that occurs in the estimation of the cost of building new nuclear power plants, I will give you. I don't think it's an engineering problem. I don't think it's an engineering problem because if you compare what we are doing in France, in what we are going to do in the UK, what Areva has been doing in Finland, and what the Chinese do with the same technology in China, you can say that, in fact, it's not completely a problem of engineering. It means that for France, it has been a long time since we did not build nuclear power plants. The last one we built was Chose 4. It was in the north of France, and it was, I guess, 15 years or 20 years before we start the Flamanville EPR. So I guess there is a conjunction of factors. We did not build the nuclear power plant for a long time. Maybe we lost some experience on this. It's just like when you say you used to be a triathlonist. You used to run very fast and to do many exercises like that, and you stop for 15 years, and then you're going to say that I'm going to be the Iron Man again. And the world has changed. The nuclear authority is very independent, is very tight, and which is a good thing for people, and because they are assessing the place in Flamanville very, very strictly, and so it causes many things, and there are many requests. So the situation is complex, and one more thing, when we built the nuclear power plants in the 80s, there was one global industry, which was the French nuclear industry. There was no Areva, Kojima, it was one big thing, and so people were working together. There was no things like, it's your fault because you deliver new things, no, it's not your, okay. There was not this part of separating things, and what we see now, we are putting things together back.
So it doesn't sound like a mathematical problem.
It's a mathematical, I would say it's a mathematical problem, but it's a mathematical problem regarding interaction in microeconomics, in industrial organization.
Okay.
What
Thank you. So we'll move on to number 2, which was really what we've heard about reducing from the decarbonize. In order to reduce the carbon emissions now, we have to decarbonize the electricity supply. We need CCS. Where's the role of mathematics in all this?
Sorry, I didn't catch your name, by the way. Jack. Actually, Jack, what you've done is you've really hit on a point, which is we not only need to consider the huge problem, but we need to think about dealing with very specific things one at a time. And each of these opportunities, if you like, for helping to decarbonise the planet has a different problem space associated with it. And it could be, for instance, improving the efficiency of vessels moving on the ocean, one problem space. And I'll just give some context for that, if people know about this. But it takes about 1 gram of fuel to move 1 ton of goods 1 nautical mile. It costs about $1,000 a ton, and annually we spend $450 billion of fuel. So it just gives a context for how much stuff we're moving about. And the costs could easily be reduced. The amount of carbon that's consumed in that domain by simply just travelling a bit more slowly, by actually doing things more efficiently. Actually, the reason that doesn't happen is an economic consideration, because if you travel more slowly, you're at the back of the queue and your asset is simply not being very useful from a commercial perspective. So solving some of those problems, one thing at a time, where we might be able to use maths either from an economic perspective, or in applying weather systems or information systems, or dealing with those logistical aspects, we can get there a piece at a time. But I do think you picked a real interesting point, which is, why don't we look at a set of challenges and, as small teams, focus on each of those individually?
And I suspect in each of those areas, then, there is a lot of mathematics involved
Indeed.
in decarbonising the electricity supply, the various aspects of that, or CCS. So mathematics is underneath that, but perhaps not on the public profile there. So we heard about extremely short-term, local short-term information being important. Alan, do you want to handle that?
I mean, this is a critical question. I mean, if you look back over the history of simulation of weather and climate, we're on a very rapid train towards much higher resolution information. You know, 30, 40 years ago, the best that could be done would be to represent the globe with grid boxes that were about 200 kilometres on a side. Today, we're predicting the weather globally with models that now have 9 kilometres grid boxes on the side. And for the UK, for example, the Met Office has a model that represents weather of the UK with 1 kilometre grid box. And it's relatively foreseeable that maybe in 10 to 20 years' time, those scales will come down another couple of orders of magnitude. So you could quite easily imagine grid boxes down to 100 metres over the UK, and globally 1 kilometre grid boxes. So as computer power and science has developed, and as the observations have increased in volume, we've been able to get to finer and finer scaling. It's only really at this stage we can really inform EDF and others what they really need to know, because we really need to get down to the scale of individual power plants, the environments of nuclear power stations, to be able to be helpful. So it's a really good question. And science, mathematics and computational ability is going to get us there, I think, eventually.
I think I'd want to move on to some other questions, Eric. We'll reserve you for the next one. Right, so could we have 2 more, please? Okay, there's 2 there. I can see the lady there and the gentleman there.
Hello, I'm Mary Lou Zeman, and you've talked eloquently about how we need to produce actionable information and how mathematicians have the capacity to translate across the disciplines and conceptualize a problem. So I'm curious to know what the mechanisms are for getting the decision makers and the mathematicians in the same room so that we can apply those skills in that room.
Okay, thank you. Yes, and one back there, yes.
Hi, I'm Steve Buckley. I was going to ask a sort of similar question, but more about how we engage the public. Because if we want I think a lot of these investments are going to be about getting the public sector to put a price on carbon, or even invest itself in some of these big schemes and take on a large amount of risk. And at the moment, there's still significant portions of the population that do not believe in climate change and don't trust numbers in general. And I think that's a big problem.
Thank you very much. Right, we've got 2 questions there, really rather similar ones, but the one is the interaction with the decision maker. So let's deal with that one first. How can we get them in the same room talking a language that they each understands of the other? Who would like to take this one? Eric, are you going to take this one?
Yeah, sure, yeah. So I think that decision makers, industry and public are all the same, right? In the end, it is the world. We just live on one planet. And in the end, I truly believe that if you just be out there, if you are visible and available to comment, then decision makers will come to you. I think that there's enough knowledge out there and there's enough understanding that math underpins this all. And so that's both for the media and for the public. And one, just to come back to the last question, which actually also is relevant here, about one key thing, which I think a big problem that is only now going to start appearing where math plays a fundamental role and where the public is extremely interested is air pollution. We are now going to have to go to scales not on the level of a power plant. We actually have to go to scales on the level of either side of the street. And what the public wants is to know when they use their city mapper or their Google Maps to know, do I walk on this side of the street or do I walk on that side of the street? That is going to happen. These apps need to be developed because it differs an order of magnitude in terms of health impacts where you walk here in London. Now, the key thing there is that it is not just about big power, big computers. Actually, this needs to run on a phone. This needs to be something that's actually done online. And that is really interesting statistics because then it is not just about throwing another supercomputer at the problem. It's actually about really smart dynamical systems theory applied to a very complex gridded structure like a city like London. If we go and address that problem, then you can watch the queue outside here of media, politicians, and the public wanting to talk to you and wanting to understand this. So just pick the right problems, and they will come.
Okay, yes.
So one of the things, in terms of public engagement, one of the policy papers produced by the Grantham Institute is called Towards a Unifying Narrative for Climate Change. And one of the sort of ideas in this thing is really, instead of trying to engage people in terms of science and equations and things like that, people will only understand a concept in terms of a storytelling. You know, that we have to develop skills in telling the story about climate change and how people should change their behaviour. I know that every time I have a cup of coffee at home, I boil the kettle at least 3 times. You know, and I've no idea why I do that, but that's what happens. Now I need to change that behaviour. I need to own that problem. And part of that is developing that story. And it can't be just the same story for everybody. People are going to come at it in a discussion with different stories. But the narrative, the strategic narrative, and that's what they talk about, has to be right. And it's developing these, trying to understand how to communicate with us all, actually, not just politicians, but, you know, as we've said, you know, mathematicians, it's our planet as well. We want to save it as well, same as everybody else, you know. So it's trying to make sure that we develop that story so that people can internalize it and sort of buy into it. You know, and I think that's really the difficult job, and it's not particularly to do with maths or science or anything. It's to do with how human beings communicate with each other, and I think that's quite a difficult thing to address.
Okay.
Just a very quick advert on the public engagement question. We have in this country a great institution, the Science Media Centre, which actually puts scientists in front of the media and also brings together policymakers as well to expose scientific evidence on really critical problems. So actually the Science Media Centre, which is based in London but actually operates across the whole UK, is a really great vehicle for doing this sort of what you're asking for, which is bringing together scientists and decision makers.
Right, I'm going to go for one more question. I probably shouldn't, but let's see who's going to ask the final question, which was going to lead us into... No, it's always if you say there's one thing, then no one will do it. Go on, yes, okay, here.
I've just been whispered at a slight point. I'm sad to see the gender balance, but I hope it will improve in the future. Sort of a little shout out for that. But that wasn't the point I wanted to make. I've been thinking as I've been listening to this, I'm a physics student and I'm a member of the MPE CDTs. I'm becoming a mathematician. And just to talk a bit about the difference between mathematics as a language and a tool and all the other subjects. I mean, it's not a separate subject, right? It's part of physics, it's part of biology. Mathematics used in biology becomes biology, is what the field is. And so I suppose when we're thinking about can numbers save the planet, can logic save the planet? Everything can save the planet, but more important is like approaching the question with whatever we need. So I wonder how you might turn that into a question, but can you talk for a second about...
I think you're giving the final wrap-up.
Okay, can we like just separate out, mathematics is not, it has to go hand in hand with other things. So what are the things that it goes hand in hand with, and what can it strengthen the most?
Right, I think I'm going to actually not go to the panel on that, because I think you have done the job. Mathematics on its own can't save the planet, but it's a crucial aspect of doing that. But it's crucial then in its interaction with others in doing that. And what we've heard about is the interaction with other sciences. It's part of those, and it's with those, and then it's with business, it's with the media, it's with the public, it's with everyone. So it's mathematicians can do it, but they have to do it with others, and they have to talk to others and know to speak the language with others. So I think I would like to thank the panel here very much for their contribution, so please. And I would like to thank you for taking part in this. And as Dan said right at the beginning, there is a reception outside. There'll be lots of people to talk to, and there'll be posters from the current students in the Mathematics of Planet Earth and Grantham Institute. So thank you for being here, and see you outside.